Hello everyone, my name is Stuart and I am the technical art tutor for the new MSc technical art course that we have at Escape Studios. Today we're going to dive into some really cool stuff with shaders. Going to learn a little bit about real-time rendering, all inside Unreal Engine. So let's dive in. We're going to be making some of these magical orbs today within Unreal. But before we get going with the practical part of this taster session, it's quite important to sort of talk a little bit about what shaders actually are, especially in the wider context of computer graphics. So what is a shader? Probably something that shades something, right? Maybe to do with some lighting equations or materials, or maybe you use it in the material graph editor in Unreal, right? But what actually is this? Well, a shader is actually, in reality, a program written for the GPU. That's all it is. You can almost think of it as being divorced from lighting or materials. It's almost just like this abstract entity. It's this little piece of code that we give the GPU, the graphics processing unit, and most commonly it's used to render pixels onto the screen. Though in recent times it can do a lot more than that, like simulations and machine learning, and we'll talk a little bit about how and why that's possible. And it has a lot of uses. So most commonly it's used for materials and surfaces. It's also used for visual effects, post-process effects. In general, if you see anything on the screen that is 3D graphics or is in some way artful, it has probably been through and contains a shader and has been through the shader pipeline. So this is all kind of comes down to a process that runs on the GPU called the function pipeline, which is a sequence of operations that we control through programs called shaders. Essentially what this pipeline does is it transforms vertices, so points in space that describe position, and also how they are stitched together in triangles or quads or things like that. It translates all of those points into pixels on the screen, like 2D coordinates. You can almost think of it like a mosaic. And this process has a set of functions. So at first we take the vertex array, we then transform it in the vertex shader, we then do some triangle assembly, rasterization, until it then finally comes to the fragment shader and then displays within the frame buffer being essentially the final screen that you see. And we control this pipeline primarily through 2 points. There is the vertex shader that works just after the vertices have been put onto the GPU and then processes them. This is mostly used just to perform some mathematics to basically project those points into the correct coordinate space on the screen. And then after that comes the pixel shader, which is another highly configurable part of the pipeline that we have access to. You also might hear this being referred to as the fragment shader, if you're using GLSL or OpenGL or Vulkan. In HLSL, that is the high-level shader language that we use in DirectX and within Unreal, this is called the pixel shader, but they are essentially the same thing. And within this shader, this is kind of where a lot of the magic happens. So this is where we calculate the colors that are going to be on the screen. So this is where any sophisticated lighting calculations might be, or texture mapping, things like that. So why the GPU? Why the graphics processing unit? Well, a long time ago, we actually used the CPU for graphics, but because of the architecture and the way, the literal physicality of the CPU, we needed to offload those calculations to a new kind of architecture. One that was able to do a lot of calculations, the same type of calculations, very, very fast. If you're talking about 1920 by 1080 screen, that's a lot of simultaneous calculations that if you're running a real-time game need to be run at 60 frames per second, 120 frames per second. It's a lot of calculations to do. So the CPU, it's got a very small number of cores, maybe around 6 to 8, depending on your budget, that can execute processes simultaneously and that can communicate to each other. So it's asynchronous. It's very good at multitasking, complicated problems. Every program that you use on the computer is in part done or is entirely done on the CPU. It's only some graphics applications that actually utilize the GPU. So you can kind of think of the CPU as, a very brainy person, but who's a little frail. The GPU, on the other hand, has many, many cores, sometimes thousands, that are all executing in parallel, but the processes can't communicate during this execution. So this is something called parallelization. So this is very, very good at doing a large amount of the same task. So for every single pixel, the fragment shader, the GPU pipeline is running and is pumping out those final pixel colors to the screen. So you can kind of think of it as a very, very strong superhero, but who's not that clever. Another important thing to understand about shaders before we dive into the practical is kind of where the way in which we use shaders and the way in which we make graphics has kind of changed, both in the final output and also how we interact with them. If we take this same scene that has been portrayed in Final Fantasy, these games have almost been about 10 years apart from each other, roughly. You can kind of see that way back in the beginning when 3D graphics were in their infancy, you can kind of see there's a much lower amount of vertices being processed. You can kind of see like all of the triangles and, the characters almost look like origami. The real-time shading that's actually going on, which are the characters, it's very flat. There's no complicated lighting. And if you wanted to do anything more complicated than that, you had to use tricks. So, for example, this background scene is actually pre-rendered. So it's almost like they've taken a very high-detailed camera snap of the scene and have then laid it onto the background, and using some kind of magic, then the real-time characters walk over it. But this background isn't being calculated during real time. So we kind of had to use a lot of magic tricks to make things work. Also, the style of them is, very cartoonized, very, not very physically based, right? So the developers here of Final Fantasy VII are leaning into not having that many resources to use. Fast forward about 10 years to Crisis Core, you can kind of see that things have gotten a lot more realistic. We have some bloom here. There's very, very much more complicated textures being pushed through. That means that the memory that we're able to put onto the graphics card within those shaders is a lot higher. But one thing that is interesting to talk about here is that although this looks a lot more realistic and like reality, we're still kind of faking a lot of these things. The lighting isn't actually physically based, it just kind of looks like it is. The shadows, for example, aren't being cast in exactly an accurate way, or the bloom, for example, isn't kind of taking into account other things within the scene. A lot of the bounce light that we can kind of see like around this train cargo container is actually painted on, and it isn't being calculated in real time from the lighting simulations. Fast forward another 10 to 15 years, and we've now got the remake, and you kind of see here all of the lighting calculations are now being done in real time, which kind of speaks to the volume of data that we're able to process per second. So almost all of this is being physically based, though there are still some tricks. The shadows are dynamic, the lighting is bouncing off of the dynamic things in the scene, i.e. the characters and the projectiles. So a lot of the graphics has almost moved from being pre-rendered or baked to being real-time and physically based. And the way that we interact with shaders has changed. So way before, back in the olden days, it used to be just primarily a graphics programmer's job. But now with the help of game engines like Unreal, we're able to interact with shaders in a much more artist-friendly way via the material graph, nodes, much more visual interfaces. But it's important to know that even though we're going to be using the material graph for this, we are still programming the shader. And you can actually view this shader within Unreal. So now without further ado, let's dive into making one of these magic orbs. Hello everyone, and welcome back to our second part on Intro to Shader Development within Unreal Engine. We're going to jump right into the practical today to learn how to make our magical orbs. It's always good before you start working on a shader to go out, find some reference. Even if we're making something that isn't necessarily realistic, it's good to have a target to aim towards, and that will help us structure and kind of procedurally go through a set of tasks. So here we've got our magical materia orbs from Final Fantasy VII, and you can kind of see there's a few things that can comprise the surface or the likeness of this object. We can see that there is this sort of texture, this kind of swirling cloud-like mass within it, and you can kind of see it's different within each one, just slightly. Each one kind of has a character. There's also a color to it, of course. You can also see that there is a glow emanating from the center of it and dissipating towards the outside. And besides that sort of that textural element, there's also the quality of the surface, exactly what's happening to the reflections on here. So this is an incredibly smooth surface, almost like a marble or something. So those are the things that we need to take into account when we're developing a shader for it. There's also other things, like you can kind of see the glow that's like cascading off of out of the orbs onto the ground. There are some particle effects, but for the most part we will be dealing with the effects that we can control through the surface of the shader. So I'm going to go into Unreal Engine, and I've just opened up the default open world level, blank world, and I'm just going to go over here to the top left, put down a shape, and put down a sphere. Lovely. Within our content browser, I'm going to right click, I'm going to click material, and I'm going to name ours m_materia. M_ for material. I'm going to click and drag it on. I'm going to open up our material editor. So here in the material editor, if you haven't seen any of this before, over here on the left we have our material preview window, and we can select from a few different surface primitives. For the most, we're going to be using this sphere, but you can go ahead and use a tube if you want. But this is probably a bit more helpful for us with our spherical materia. Over here underneath it is the details panel, and this will change depending on what node you currently have selected. If you've got nothing selected, then this is essentially the defaults for the material within Unreal Engine. So this kind of has lots of high-level toggles and controls that you can make use of for various kinds of effects. We're going to leave that alone for the most part, and you'll see how that changes as we add more nodes. Over here on the right is the node graph, and so this is where we will be adding in all of our logic to drive our effects. Over here on the right is are the output parameters, the outputs of the shader that we are developing. We have base color, the metalness, the specular, the roughness. You don't need to fill in all of these, just a few of these can sometimes get you the effect that you want. So we will be working our way through a few of them to get the effect of the material. So the first thing that I'm going to do is I'm going to hit Tab. You can also right click within the material editor to start laying down a node. And I'm going to put down I'm going to just start typing, and I'm going to put down a texture sample. So you can see here, when I don't have this texture sample node selected, we have our default details here on the left and details panel. But when I do have my texture sample selected, it then changes. So these are the details, essentially the parameters where that we can change this texture sample node from. And these also slightly correspond to these input pins here as well. So we can just change them without having to supply it with new arguments. So if we click none, I'm going to type in noise, and I'm going to select do we have a Perlin noise? Yes, wonderful. Okay, so we currently have our texture sample, and to preview this, I can right click and I can say start previewing node. And this will preview our material on our sphere. Or this will preview our texture, or whatever node that we've currently right clicked and previewed. This will preview it within this preview window, thumbnail window. So I'm going to stop previewing it, and I'm going to stick this within our base color. Okay, so you can kind of see this is sort of already looking kind of cloud-like, similar to our material reference here. But the biggest thing that I can see is that obviously our orb needs to be colored. So let's add in some color. So I'm going to add in a constant 3 vector. So a 3 vector, you can kind of think of it like 3 numbers that together make one single variable. So these could represent a lot of different things within computer graphics and shaders. It can represent an XYZ coordinate in Cartesian space, or it can also represent an RGB value, red, green, blue. By default, the Unreal Material Editor previews them as RGB values, but you could put these in and do some offsetting or other like spatial calculations with them. These are just numbers. So I'm going to select a nice bright green color here. You can see that if we put it into the base color, it makes it green. Now, obviously, I almost want to like mix these things. I kind of want to have this texture, and I also want to make it green. So to do that, I'm going to put down a linear interpolate, or a lerp node for short. And you can kind of think of a lerp as a way to blend between values. So for example, if I click this here, and I'm going to duplicate this. So if I click on my color and I hit Control D, I can duplicate it. Okay. I'm going to start previewing this, and I'm going to make this a much darker value. So here I have my dark, almost black value hooked into the A parameter, and B is hooked into this green. The alpha value, that will kind of be the thing that determines if we go more towards A, the value in A, or more towards B. So the closer it is to 0, the darker this color is going to become, and the closer to this A value it's going to become. When it's 0, it is completely that value. And inversely, when we go towards 1, it becomes more green. Now we don't need to have a constant value in here. We can in fact hook up our RGB texture sample into it and put it into our base color. If we stop previewing it, and as you can see, where there was black within our noise texture, there is our, value of 0, black is also 0, there is this dark value. And when the value is 1, or that white, the value is this green. As you can see though, our material still hasn't taken that into effect. So if you click the save here, it'll then take effect within the world. Alright. It's looking pretty good, but I kind of want some more control with my texture. I don't want to just have it be determined by the image that we're reading in. So to do that, I'm going to add in some controls. Now, the values that are coming out of this RGB pin they're just numbers. And so like any number, we can perform mathematical operations on it. And then when we visualize those numbers, you can kind of see how they're then translated into something meaningful. So for example, I want to add some contrast to this. So I'm going to add a power node in. So I did that by clicking and dragging off here and then typing in power. You can already see that by adding a power node in, it kind of adds more contrast. So as I increase this, the lighter areas will get brighter and the darker areas will get darker. And this is essentially saying whatever value is coming out of here, we're going to multiply it by itself to the power of, well, we're going to perform a power of operation to the power of around 4.182114. You can do other mathematical operations on this. For example, we can perform an add. If we preview this. And so adding is taking all of those values, say we have a value of 0.5 and we're going to add then 0.3 to it. So it then becomes 0.8. So it's kind of like a brightening or a darkening. So if we add a minus number, for example, it darkens everything. And if we darken to basically to 1, it'll make everything black because all of those values are darker than, are less than 0. I'm not going to do that for now. For now, I'm just going to have our power. Okay. And I'd quite like to be able to access this control for our power in an easier way. So I'm going to right click here and I'm going to say promote to parameter and I'm going to call this contrast. So when I made that, it then put the value to 0. And you can see here in the parameters tab, we now have our global contrast parameter. And if we increase this back to say 2, you can see we now have a simpler way to interact with our shader. And so in general, as we're going through it, you want to be adding parameters to this details panel that are going to be the things that sort of control the shader the most. So it kind of simplifies things for users of your shaders. So we don't need to just perform mathematical operations on textures with powers and additions and subtractions. We can also do it with other textures. So for example, if I click and drag this, I duplicate it, and let's change the noise to something a little bit larger. Let's try this. Okay. So now, if I take this and multiply it by this, we're going to need to add a power in here, just to add a little bit of contrast again. You can kind of see that if we, for example, let's just promote this parameter, call this contrast 2. And then it just took everything up here. All right. So with the contrast, with a contrast 2 value of 0, we're actually not multiplying by anything right now. But if we increase this value, you can kind of see we're getting these darker areas now. And so by using these two textures and multiplying them together, we're able to get both shapes, essentially. So this overall okay, for the sake of consistency, just going to break this, delete it, and I'm going to parameter and then call this contrast 1. Okay, something like that, I think. Now, to make sure that the value that we're getting out of here is constrained to the range 0 and 1, I'm going to just pop this out and I'm going to put a saturate node down. So all saturate does is it makes sure that our values are between 0 and 1. So it's kind of just good practice, especially when you're going to a lerp, which tends to do funny things when it gets outside of that range. Okay. So I'm pretty happy with the texture that we have here, but if you see on these materials, there's also the kind of the glassy surface. So let's deal with that very quickly. And so we're going to use these specular and roughness values, and I'm going to just click 1. Well, I'm going to hold 1 and then left click within here, and it'll make a constant of 1. I can also hit 2 and make a 2 constant, or a 3 and make a 3 constant, or an RGB value. I'm going to put this roughness into 0. I'm going to put this 0 into roughness to make a perfectly shiny, unrough object. I'm going to then duplicate this, put the value to 1, and put this into specular. So together, these two values kind of almost make up the shiny quality of our material. So the roughness dictates, of course, how rough it is, and the specular, you can almost think of it like the intensity of the reflection. So as this, for example, gets towards a 0 value, you can kind of see we're seeing less of the surrounding area. So I'm going to keep that 1. And now if we save. Okay, so our magical orb is looking pretty good right now. So now that I've done the surface quality of our material, I'm going to click and drag and tap C for comment. And I'm just going to label this diffuse color. And just generally do a little bit of grouping and housekeeping. So Control C, or just C, and I'm going to call this reflection. And then I'm going to click and drag, and then click C, and call this noise texture. Okay. So in addition to our surface texture, we're going to kind of add just a little bit more character to it. So to do that, we're actually going to animate the texture along the surface of this material. And you can do that using UVs. So UVs are kind of like the coordinates that the texture is using to map onto our geometry here. So you can kind of almost imagine that each point within our sphere keys to a different value within the UV space, and then it's almost like you're wrapping a tangerine or something like that with this image. So by increasing those values or distorting them in some way, we can place them by hand a little bit more, but we can also animate them. So to do that, I'm going to hit Tab, and I'm going to type in text coordinate, and I'm going to put it into our UVs. And you can see that nothing's happening. That's because Unreal Engine automatically supplies the default texture coordinate to the texture sample node. So you can see here that this node is red, which means that this is data that is coming from outside of the shader into it. So these texture coordinates are coming from the mesh that we are currently using to material. So to actually do something with this, I'm going to put an add. I'm going to click and drag, and I'm going to add time. And you can see that for every, essentially like for every second that's happening within the game world, we are adding that to the texture coordinates in the UV space. And so it's looking like it's going towards the top left. Let's kind of slow things down a little bit. I'm going to multiply by value 0.1. See how that is. It's looking pretty good. I'm actually going to do a little bit less. Yeah, that's a little bit better. Okay, and I'm gonna click and drag and then press Ctrl and D and do the same for our second texture as well. But we're going to add we're going to multiply it by a different value, so it's going the other direction, say minus 0.1. And so with these two textures now being animated at different speeds and in different directions, you can kind of see our balls looking a little bit more magical. Great stuff. So again, I'm going to click and drag and I'm going to hit C. I'm going to call this texture anim. Now that we've done that, you might notice that, of course, there's one critical piece that is missing from our magical orb, which is the glow. So to do that, we're going to use a node called Fresnel. That is spelled as F-R-E-S-N-E-L, Fresnel. When we start previewing it, you can see that it is white on the outside and it gets darker towards the center. And no matter what our viewing angle is, that's always the case. So essentially this is doing some maths with the normals of the vertices around the sphere, which is, you can almost think of normals like the, it's kind of like the direction that the surface is pointing at that point within it. And so it's using some maths with the surface normals on that sphere and the camera to know where there are edges that are at a 90-degree angle to it. So this is kind of looking a little bit glowing, but obviously we kind of need something a little bit different, so almost the inverse of it. So we're going to do a 1- here. And I'm just going to play with these values until we get something a little more pleasing. So I'm going to put a value of 0.1 in here. So you can see now the center of our sphere looks like it's brighter and the outside is in dim part. So 1- takes whatever value you're putting in it and does 1 minus that number. So it kind of inverts things, especially if you've got a range between 0 and 1, it basically inverts it. So I'm going to stop previewing it and I'm going to put a power here. I'm going to just use this to kind of sculpt the fall off a little bit more. So I'm going to raise this because I want it to be really bright in the middle and kind of fall off like quite quickly. So again, this is kind of like it's adding contrast to that gradient. Now we're going to take that value, we're going to put it into the emissive color. We're going to save, and we're going to stop previewing the node. Well, I mean, there is a glow, but there are a few things that are wrong with it. I mean, for one, it's very, very tiny, and for another, it's kind of almost being drawn over all of the other things, all of the other parts of our shader. So to solve the brightness, we're just going to do a multiply, and we're going to right-click, we're going to promote this as a parameter, we're going to call this glow intensity. Let's spell that correctly. City, there you go. And we are going to just crank this value up. Yeah, be around something like that. Now a good trick here that we can do is before the glow intensity, I'm going to add another multiplier in. And this time I'm going to multiply this with the output from our lerp node up here. And if we increase this you can now see that our glow is only coming through on the lighter green areas and not on the dark. So it kind of almost looks like it's inside and it's being included by these dark bits of energy that are swirling around it. Okay, amazing. I'm pretty happy with that so far. And in terms of how closely it matches our reference, I'd say this is pretty, this is starting to look like something that we could potentially use within our game. But let's go a step further. I'm going to click and drag, I'm going to hit C and call this glow. And I'm going to just add just a little bit of dust, a little bit of spice now, and kind of try and make this our own. We don't want to just be blindly copying from Square. So I'm going to get a texture. And then I'm going to get a nice kind of rocky looking, normal map. I'm going to put this into our normal value. You can already see with just that, we're now affecting the normals of the sphere. So like I was saying before, normals are kind of like they are the perpendicular direction of a surface. So say my hand is a surface here, the normal would be if I was to put a pen right through that at 90 degrees, that is the direction that is the normal of that surface. And normal is just a vector, so it has x, y, z coordinates. And just like we've all been saying, x, y, z coordinates is just a vec3, and another way that we can represent this is with RGB values. So that's why UV and normal maps kind of look like this purpley cyan color, because the x represents red, the y is green, and the z is blue, RGB. So we can see that by if we take this normal map and we get rid of everything but blue, for example. So now this is just the Z. So now that we have our normal map, I'm going to save it. And here we are with our final magic orb shader. One thing I forgot to mention, as I was saying in the theory part of this, even though we are interfacing with the material graph within Unreal, we're still writing a shader, and you can actually see that shader code that we've been generating. So if you click up here in the top left in the window, go down to shader code and click HLSL code. If you copy this is then basically all of the shader code, or the HLSL code that we've actually been generating. And it's enormous. It's because most of this is the inbuilt stuff within Unreal, and very little of it actually is the other nodes that we've created ourselves within here. So I've got a notepad up, and if you go to, try and find Control F, pixel material inputs, you can see we've got emissive color, opacity mark, base color, all of the things that essentially are being output within our material over here. So we can almost kind of reverse engineer this to see where we have affected things. So you can see here in the emissive color, it's being assigned the value of local 31, and local 31 is just up here. And in between that, we're doing alert between local 30, pre-shade buffer, and another pre-shade buffer. So let's just have a look there. So if we click that, so if you keep kind of going through the material, so local 30, local 29, multiplied material float, pre-shade buffer. So these pre-shade buffers, they're kind of like storage numbers that are being stored within the shader. So we can kind of safely ignore that. So local 29, okay, local 13, local 28. Okay, so we're doing a lerp here. That's kind of looking like something. So Let's try and actually find a number that is significant to us in some way. So here you can see we're doing a positive clamped pow, so that's probably a power with 4.0764780. Right here, that's our force 4.0764778. So this local 13 is actually our power. Now this is a little bit hard to read. If you're watching this tutorial, I suggest that you root through it and try and figure things out for yourself. It is pretty dense and a bit of an advanced thing, but for now it's kind of just enough to know that we are generating code through doing this, and this is very much what is then given to the GPU when we come to creating our real-time graphics. I hope you enjoyed this lesson on shader development, and for more lessons like this, visit the rest of our channel. See ya!